So I've got a new interesting drive here. It's the integrated servo drive with EtherCAT. It's kind of designed for the back of a motor, but it's got a hole in the middle, so that's interesting. We can run cables through it. So the connectors are for power coming in, power going out, 24, 48 volts. It says 60 volts here, but typically we'd use like a 48 volt supply. 3 motor power wires going out. There's a connection for earth here on the mounting holes. We've got some EtherCAT in and EtherCAT out. We've got serial. We've got absolute or differential encoder, like a Biss-C, clocking data, or differential incremental. Halls, single-ended, encoder, single-ended, and some I/O. Maybe we fire a regen. Maybe we take an analog input on a load cell or some haptic device. You've got the FETs. There's no heatsink here, but it does 15 amps continuous, 30 peak. If things get hot, there's a heatsink option. So I found a motor with a hole in the middle too. So this is a harmonic geared harmonic drives motor. This says 24 volts, but they also make a higher voltage winding, but I'll use it today with 24 48 volt power supply. I've got the FHA-8C. So this is the motor model number, and you can see that there's various gear ratios, 100 to 1 gear ratio. I've got a 30 to 1 gear ratio here. US is incremental encoder. Incremental encoder 200 is for 2000 line. Times 4 is 8,000 counts per rev. And of course the E option, very important, 24 volts. If you don't have the E option, it's not for 24 volts. It's for higher voltage. So we'll take a look at the motor here. I got the XP power 48 volt supply, and I got my power running up through the hole in the motor, through the hole in the drive, and coming in to this node. And I've got the motor and feedback wired here. These little Hiroshi connectors are a pain in the butt, but there's some flying lead wires with pins on the end. I cut them in half, pop a pin in, strip it back, and get it connected to the motor feedback. So that wasn't too bad. I'm using a USB to serial connector. This is a -M, SER-USB-M. I took the RJ11, clipped it off, and put my own connector on. These pins are a little bit bigger. They're Molex, so those are a little easier to connect. And of course, I have the ohm meter here, which I'm going to use to measure the winding resistance, because I'm not in great belief of the motor data that I was given, so we'll double check that. If you're looking for the software to do this, it's on the partner resource page. You enter your email and password. You can get this from your local distributor. He can send you the link, or the local distributor can get his username and password from customer service here. So I'm looking for the CME beta. I downloaded the 8.0 beta 17, which allows me to talk to the IES drive. Yes, you need new software for a new drive. So we'll go through the basic setup here. I've got a brushless rotary motor, no brake, and this one is not vertical. Incremental halls, halls with incremental encoder, 2000 line, 8,000 count. If I had a brake or needed a controlled stop, I could set some times here, maybe put in a speed and the time it takes for the brake to engage, or I guess settle. Position mode, I always like the EtherCAT or CANopen stuff. This is EtherCAT drive. Sinusoidal commutation, that's fine. We'll take a look at the motor. And again, I got the motor spec here. I don't believe the back EMF constant or the resistance, so I measure it with my ohm meter, the winding resistance, okay? And it's like 1 ohm. So let's take a look for 1 ohm 8C. So here it is, dash E. Okay, so the other one is for like the 100-volt motor or the 200-volt motor. Well, that's more like it. 1 ohm, 3.2 volts per kRPM. The torque constant, back EMF, same value for volts per radians per second. It says I can go 6,000, little tiny torques. This is at the motor shaft, not at the output. The output torque multiplies by the 30 that's in the gear. And the speed divides by 30. So the output can't go 6,000 RPM because it's at the end of a gear, a harmonical gear or a harmonic gear, a wave strain gear. Anyways, got the good data. I hit calculate. It calculates my peak and continuous currents and all the gain values based on the good inertia data I put in, assuming that's correct. And we'll look at the current loop here first. So does a little 100 hertz steps, goes out, rolls off 500 hertz. Maybe I should do my current loop tuning, but you know, check your motor continuous current and compare that to this is, if the motor's amps RMS, then you multiply that by square root of 2 or 1.414. So this should be sufficient current. Velocity limit says 3,000. I can set it to 6,000. Like that, so let's leave it there. I don't want to prematurely limit. So I'm just going to go through a little tune of the current loop here first, because I don't have any faults going on here. So give it a quick little tune. Ringing. Cut it in half. 800. Okay, so if the current loop's too big, you get, look at the overshoot. That's the overshoot right there. Cut that in half. Maybe a little bit high. Knock it down just a tad. There, that's good. So now I should have an improved current loop bandwidth. Of course, I like 1.2 kilohertz plus or minus 200 hertz of current loop bandwidth. Higher speeds, more bandwidth, lower speeds, less bandwidth. Never have more bandwidth than you need. 1.7, that's a little hot, but we'll just leave it alone. Looks pretty good. Good idea to phase the motor. So we have 5 pole pairs, or 10 poles. And I'm going to try to rotate the motor with 10% of the current. Hey, look, it doesn't move. That's because the current's too small. Let's do the full 2 amps. All right, here we go. Now it's moving. So the electrical cycles are rotating, and I don't see the motor moving much because it's a 30-to-1 gear. But what I do, oh, look at that, there's a Hall offset. So I'm going to try subtracting 60 degrees. Slight lead in the forward direction, slight lead. When I go forward, do the counts go up? Yes. Watch it again. Counts going up. So the black indicator is the current vector, micro-stepping in a diagnostic mode, and the Halls are decoding and the encoder's going up. 5 revs of the dial will equal 1 rev of the motor, and 5 revs of the dial should land us on about 8,000 counts, and that must have been where I was when I started. Anyways, I got to do that 30 times to see the actual motor output spin. We'll do a much faster rate, and oh, you can barely see it. It's moving 1/30th of a rev, right? One rev per second divided by 30. So that's like the second hand on a clock there. But it's moving. You can see it move. Pretty cool. So this is good phasing. I'll say OK. Let it save to flash. I got some tuning values here for the current loop. So I'm going to save the hard work I did on the current loop to flash. So let's take a look at tuning the velocity loop here. We'll set some profile. That seems pretty good. You know, we could cut it down a little bit. If you had a big inertia, you might want to make this smaller. Okay. Auto setup checkbox, limited velocity, actual motor velocity. I like to look at current, actual current, and 600 RPM. I'll just slow it down here. Bang, bang, back and forth, 3 hertz, hit start. So we can see it wiggle a little bit at the output. That's not 300 RPM at the output. That's at the shaft of the motor inside the motor. So divide that by 30, so 10 RPM. So if the gain's too high, you break into oscillations. If you break into oscillations, cut the gain in half. I'm 23. Let's try that. 30, 1, 2, 3. I need more gain. So what I've got is gain shift going on. I'm going to undo that. Little integrated wind up there. So now I've got high gains again, small numbers. So looking for the oscillation. I double it till I see it, makes a loud noise, and I cut it in half. There it is. Woo, act cool. Cut the gain. You see the oscillations? Gain's too high. Let me show you another trick here too. This is heavily filtered, no resonance. If I make a single pole filter and apply, what I might see is less buzzing. There you go. So before I couldn't do 400. Now I can. So, you know, it depends on where the resonance and poles are. It's still a little buzzy, so cut it in half. Lots of gain margin. We like lots of gain margin. And then we'll do the integral. I'm just going to set it here. It's probably too high. I don't see any integrated wind up or anything. Maybe it's fine. Too high. I really adjust the integral more in the position loop. It gets rid of the it gets a better settling time. So yeah, integrator wind up. It's too big. So we'll just set it here for now. And we're going to do a position move. 8,000 counts is a single rev. 3 times 8 is 24. 24, 3 times 8, 24,000, another 0. Ah! There you go. 1 rev of the motor is 8,000 counts times 30, 24, 240,000 counts is a single rev at the output. So we can, let's just jog it a little bit so it's back up here. So little jog, and then stop. Okay. So settings tab, still waiting. Stop. Oh, auto setup checkbox. Sorry. 24,000. Profile velocity following error. Let's look at the current. Actual current's always nice. Let's not fill it up too much yet. And we'll take a look at that. That took too long. Too short a move. All right. And we'll look at the settling time here. Oh, so the integrator's fine. Yeah, maybe. I've never set the integral that high before, but there's no load. You know, integrator comes down when the inertia gets bigger. A little too much integral. See the overshoot there? That's bad for settling. Takes too long. Try it again. We'll move. So, still too high. Give it 600. So again, sort of the fine tuning in here. There's a feed forward term, but that just, you know, corrects the error while we're moving. That's a perfect move and settle. If I had a big inertia, like 100 to 1 gear the inertia ratio is like square root law with a gear. So 30 times 30.